Thank you all. I just want a fast raise of hands. Who here knows how neutrino oscillations work? Because depending on that, okay, so 50%. So we're going to relatively fast on this then. So I just want to have some notes that for those who have not seen neutrino oscillations before, could be useful. And for those who have seen it, maybe it raises some questions. I'm most very nervous about this derivation because it's actually much more subtle and tricky than what I'm going to show you. But I hope this process some engaging discussions. So neutrino oscillations are going to be essentially a quantum mechanical phenomenon in macroscopical scales. And they're going to arise from the mismatch between the neutrino weak eigenstates and the neutrino mass eigenstates. And we're going to talk about what that means in a minute. So let me just my other notes. Okay. Good. So in the standard model, the neutrino weak interactions are essentially given by these two terms. So there is this term here that tells you the interaction with the charge current processes. So this one here. And then there is also this term here that tells you how they interact with the neutral current exchange. And in pictures, I'm omitting couplings and some things here. And on pictures, they look like that. And so what happens is that the neutrino mass states and the neutrino flavor states are not eigenstates of the same operator, but they're actually related. And we typically we relate them by a matrix, which we call the Pontocorvo-Maki-Nakata-Sakawa matrix. And that matrix is nomenclature is P-S. And we denote the flavor states typically as just nu alpha, where alpha denotes the flavor index. And our convention is that these flavor states are going to be some kind of superposition. So it's going to be a sum over the mass states, which I'm going to denote by nu I. And here the fact that I'm using this matrix as complex conjugate is just conventional in nature. So these are going to be my mass states, and these are going to be my flavor states. Okay. So when we produce a neutrino through a weak process, for example, when you produce a neutrino through pion decay, which is our most discussed decay type in this lecture series, we produce exact weak eigenstates. So in diagrams, we think that that means that you have, your pions, it goes to a W, and it produces this pair here. So what does this mean in terms of these superposition states? So what happens is that in reality, when we produce a neutrino state, we can actually not kinematically measure its mass. That's because the neutrino mass is much smaller or smaller than 1 electron volt, and that means that I can actually not know if what I produce was a muon plus a nu1, or a muon plus a nu2, or a muon plus a nu3. So in those situations, we say that there is a superposition of states that are being emitted from this decay. And so how we can depict this is that we say that this decay is essentially the same as having something like W muon and then nu1, or we could have W goes to muon plus nu2, or W goes to muon plus nu3, right? And so I just cannot differentiate between any of those. And the relative amplitudes of these processes are going to be given by mixing elements. So that means that these diagrams are then weighted by, for example, here would be U star mu1, U star mu2, and U star mu3. Okay? So that's what we mean when we produce a muon neutrino from a pion decay. What comes out of it, because of the fact that I cannot measure the kinematics with infinite precision, I get this state out of it. Okay. So then what happens? So then what happens is that you start with some initial neutrino configuration. Okay, so let's say that that's a mu neutrino or some fixed neutrino flavor states. And then what's going to happen is that's going to time evolve according to some Hamiltonian, and I'm going to end up with the neutrino state at some time t. And so for definiteness, say that we start with given flavor states. This is going to be essentially the case for more cases, like we have beta decay or pion decay or whatnot. We are going to have, for example, in the previous example, a mu neutrino. And then the neutrino state at some times t is just given by this expression. This is just basic quantum mechanics. So if the neutrinos are propagating in vacuum, that means that this Hamiltonian that's associated to the neutrino time evolution is just going to be the kinetic energy of the neutrino. And that means that each of these mass states will have a well-defined energy, which I'm just going to call E sub I. What does that mean in symbols? That means that if I apply this Hamiltonian to the new I get some energy eigenstate times my new I, right? So there's definition. And so then what you can do is compute the time evolution, right? So I apply my time evolution operator to my neutrino states. This is my initial flavor state written in the mass spaces. And so I can just apply this operator over the sum, and I get this thing here. And then you end up that this operator is applied over your mass states. And so what you end up getting is something like sum over I, U alpha I star, E minus I, E I T, and then you get nu I, okay? So that implies that each of your neutrino states now acquires a phase, and that phase is going to be distinct because of the different energies that the mass states have. Okay. So then if I want to compute the amplitude from going to flavor alpha to flavor beta after some time t, that is just given by this bracket here. And if I can expand this directly, this means that this is this observable or this state being applied to my time evolved state, which is this. And these states, you can decompose it further into mass states. And so then what you get is you're going to get something that looks like something like a double summation on ij. And you're going to get something that looks like U j beta, U alpha I, E I A I T, and then you get nu j, nu I star. So something like that, right? This is just very basic quantum mechanics. And because the mass states are orthogonal, this thing here is just going to give you a Kronecker delta, ij, and then you go and collapse that summation. And then you end up that the amplitude from going through flavor alpha to flavor beta after some time t is given by this expression here, which just depends on these matrix elements, mu, u's, and the energies of your mass states. Okay. And then the probability, you just have to follow the quantum mechanical recipe. So the probability to get the probability from the amplitude, you just have to square this here, and then you're done. We're done. That's it. Okay. So now my problem is, what's this EIT state here? So in 3 flavors, it's a little messy. So I'm just going to do it in 2 flavors because that captures the main features I want to use for my lectures. But you should do it in your home for 3 flavors because it's a nice exercise. But in 2 flavors, you have that the mixing matrix can be represented by just something like cos theta, sin theta. So cos theta, sin theta, right, minus sin theta, cos theta. So notice that this is actually a real matrix. In reality, the PMNS matrix that I had before was a complex matrix. You can prove that in 2 flavors, you can always remove the complex phases out of it, so you create a real-only matrix. And that should be an exercise that you should think about, like why is this only real, is something that's actually a neat question. And then, of course, then what this implies is that, for example, your new E states will just be given by something like cos theta, nu 1, sin theta, nu 2, and then minus sin theta, nu 1, plus cos theta, cos theta, nu 2. Okay? And then if I want to compute the amplitude, remember that the amplitude was this state here. That's nothing else but my final state, which is just the new E. Okay, so that's just this. I just copy this here. And then the timeable version of my mu state. And that's just going to be the state with some phases written in there. So that's going to be minus E minus I, sorry, not H, E1 T, nu 1, and then you get a sine here, and then a cos theta, E minus I, E2, T, nu 2. Okay? So nothing fancy here. And then you can multiply this out, do some algebra, rewrite it, and you get this expression here. And you notice that this expression has this here, which is an overall phase. And there's a sine and a cosine product. And then here, what I want you to appreciate is that now I actually have the difference in the energy eigenstates of your different mass states. Okay. Then you have to compute the probability from mu to E. That's given by essentially the amplitude square, which you can rewrite like that. I'm not going to bore you, but you can just multiply things out. And in the end, what you're going to end up after you do all of these multiplications is you're going to end at something that looks like sine square 2 theta sine square the energy difference T divided by 2. Okay? So this is just algebra. And so that is then the probability to change between muon to electron state after some time t. So you see that it depends on this mixing amplitude here. That's just given by nature. And then it depends on this energy difference here. So now my question is, how do I find out what the energy difference is? This is where things get a little shaky. Let me be entirely honest. But we're going to follow a simpler approximation where the neutrinos have well-defined momenta. So the neutrino energy, like the relativistic energy in general is given by this, right? And so that means that the neutrino energy is approximately equal to the momenta. Here I mean the magnitude of the momenta, plus m squared divided by 2 times p. Okay, assuming that the momenta of the neutrino is much larger than the neutrino mass, which is true for all purposes. Essentially, is always true because neutrinos masses are, as I was saying, less than an electron volts. And neutrinos are produced either in beta decay, which has energy scales of nuclear processes. That means it's going to be MEVs versus EV. It's a factor of 1,000. Or it can be produced by pion decay. And in that case, you have energies of scales of hundreds of MEVs, definitely much larger. So essentially, there is no regime where this is not true, except for one scenario. There's only one case where this is not true, which is for CNOV neutrinos, because CNOV neutrinos have been cooled down by the universe expansion, and in that case, it's not true. So except for CNOV neutrinos, this is just fine. And so then, that means that the energy difference of my states is just given by assuming that the neutrino momentas are similar. You get that this is just the difference in mass squares divided by the momenta of the neutrino. And we often write that this is the mass square difference divided by 2 times the energy or the mean energy of my neutrino beam, or the energy of my neutrino. And that leads us to this classic equation that you've probably seen in many talks that says you that the oscillation probability from going to 2 flavors depends on the mixing element square times 2. And then it depends on sine square delta m square. And then assuming that the neutrinos essentially go at the speed of light, which is a good approximation, that gives me L over 4E. Okay? And so you end up with this appearance probability relationship. So now, not much secrets in this. This is actually what you will end up using most of the time. I must warn you that this derivation is technically wrong. And the reason the derivation is technically wrong is because in doing this derivation, we've actually assumed that the neutrinos are plane waves. So they have well-defined momenta, which means that they are actually delocalized in space. That's actually not true. When you produce a neutrino from a beta decay, that's actually localized in the production region, which means that there is actually a finite distribution of momenta included. So the correct way to do this distribution, or one of the ways of doing it, is by using something known as a wave package treatment. It turns out that, this is wonderful, it turns out that if you actually do the complicated calculation in the regimes of, any regimes that we will discuss, and actually any terrestrial measurement, to first order, this actually holds. Okay? But for the caveat, this appears very simple, but it's actually they're simplifying assumptions that are non-trivial here. Good. Okay. So there are essentially 4 important things that, I want to say 4 or 3? 4. 4 important things that I want to remark on neutrino oscillations. First of all, the amplitude of the neutrino oscillations is going to be set by nature, and it depends on this matrix U. Okay? That's something that I can, in principle, not control. It's given by however the universe decided to give us fundamental constants. There is a small caveat to this, that you can change this in matter. We will leave that on the side for the time being, because we're talking about astrophysical neutrinos, things operate in vacuum, so we're not going to worry about it. Another important is that the neutrino oscillation are going to be periodic, at least in vacuum, and that is going to be a period that is going to depend on the ratio of length to energy. Okay, so that's going to be our oscillation scale. And then the third important point is that there are 3 important experimental regimes. The 3 regimes are like schematically shown in this diagram here. Remember that you have a formula that looks like sine square of delta m square L over E times 4, and then there is a coefficient in front of it. Right? So this oscillation here is going to depend on this quantity. So when L over E is small, the transformation probability goes to 0, which means that the neutrinos do not change flavor. And so for a small L over E, no oscillations are observed. The reason is that there is not enough length for the oscillations to develop. You need to have farther spacing. Then here is the location of what's known as the first oscillation maxima. So making neutrinos in the laboratory or at Earth is expensive. You have to have a powerful beam to make them. And if you have a neutrino beam and you put your far detector far away, you lose flags like 1 over L squared or 1 over L to some power, depending how focused the beam is. So you typically don't want to put your detector too far away from your source. So most neutrino experiments want to work in positions that are either in the first or maybe the second oscillation maxima. Okay? If you have, in principle, an infinitely strong neutrino source, you could be anywhere you want. And then as the L over E increases, the oscillations become more and more rapid, and we end up with a third regime, which is the regime where, oscillations are averaged out due to finite resolution in L over E. Okay? So I have an error on my length from my detector position to detection. I have an error in my neutrino energy resolution. That's actually going to involve an uncertainty. When you convolve this line with that uncertainty, that's going to smooth out an average of these conversions. And so what you're going to end up is you're going to end up with some average behavior that for the 2 flavor approximation is going to be like a half of sine squared to theta. Okay, because the average of a sine squared is just half. Okay, so that's the 3 regimes. Essentially, I see no oscillations if I'm too close to my source or if my energy is very, very large. I can optimize the MA detector to be in this optimal location to see the maximum oscillation behavior. And if I overshoot or my resolution is just not good, I don't see anything. I just see like a constant depletion of my flavors. Okay? I will often use the word flavor transitions to refer to this sort of regime, just to emphasize that there is no energy features that are that important for this regime. Another important point, and I will emphasize this in some slides in a couple of minutes, is that neutrinos are natural interferometers. Oops. So what do I mean by that? I mean that neutrinos are actually sensitive to the contents or the matter that they are traversing. So for example, in the Earth, we have electrons that are in the atoms. So when a neutrino crosses through the planet, there is this term here that produces a coherent forward potential, or a potential that comes from this coherent forward scattering. And this potential actually modifies essentially the energy of your neutrino states. And so your Hamiltonian in vacuum is given by this. It looks a little more complicated because I'm writing this in flavor space. So this is in mass space, and this is just converting to flavor. And then there is a term that's going to be an energy term that's going to be proportional due to these interactions. So this is going to be something that is a potential. Oops, no that. This is a potential that is sourced by the medium. Okay, and so it turns out that the size of the potential is going to be proportional to the strength of this interaction. And so the strength of this interaction is given by G Fermi, and then the number of electrons that are at a given time. And so it turns out that this term here is going to be something like G Fermi times number of electrons, and then zeros in the other flavors because there is no muons or freely or abundantly in nature or in a stable fashion. And so then you have that the neutrino eigenstates or the neutrino energy levels are modified by these, and these are known as matter effects. And so they're really important in the case, for example, of the sun. Solar neutrino physics doesn't make sense if you don't take this into account. In the case of neutrinos in the atmosphere, they're going to be less significant. But for the high energies, in some cases, they will start being more relevant. And the reason is that as your neutrino energy increases, this kinetic energy term here is proportional to 1 over the momentum of the neutrino, which means that as the neutrino energy increases, the contribution from the subdominant interaction term starts to become dominant part of the Hamiltonian. So at high energies, essentially the Hamiltonian is given by whatever interactions the neutrinos experience with matter or anything around the path. Are there any questions so far? Yes? No. It's because I have actually removed a constant phase out of it. When I do that, I actually took this P out of it, so I'm subtracting that. Okay. Yeah, so
can you repeat the question? Sorry.
So let me repeat the first question. So the first question is, why doesn't this scale like P squared over 2m, which is the classical kinetic energy? And the answer is that what matters is not really the energy, but the energy difference. And the energy difference actually scales like m over 2p squared. And the second question was, I forgot the second question now. Yes. What happens if your source is too far away? if you should put a 1 plus c factor here, and the answer is yes. You need to redshift your energy to come for that. So really good questions. Good. Okay. Any other questions on this? So if you have never seen this calculation, I invite you to do it. And if you have seen this calculation, I invite you to do it in a more difficult case, which is the case of wave package, which many of you may not have seen it. Okay. So now, what's important for us? So there are actually 3 neutrino states, which means that there are 2 mass square differences that are relevant for our discussion. One of them is this mass square difference 2-1. And we know that from measured from reactor experiments, also solar experiments, and that is about 7.4 to the minus 5 electron volt square. Then there is a larger mass square difference, which we call delta M squared 3-1. So that's the difference between the third and the first mass state. And that one is plus minus 2.5 to the minus 3 electron volt square. And so this minus sign is actually important. So we talked about this in terms of the neutrino ordering. So that's not a nice line. So one possibility is that your neutrino states have the following mass ordering. So they could be, let's say, nu1, nu2, nu3, and this is increasing energy or mass square, like that. So we call that the normal ordering. And there's another possibility that the actual mass spectra of the neutrinos looks like this. What is nu1, 2, and 3? Oops. 1, 2, and 3. Okay? So we call this the normal ordering, and we call this the inverted ordering. Also, people call it the abnormal ordering too. And this is because in the quarks, masses are ordered like that from hierarchy. So we actually do not know the neutrino ordering. So we do not know if the neutrino mass states are like that and like this. Okay. So that's why there is a plus minus in this 3-1. The relationship between the first and second mass states is actually known from solar neutrino measurements because there is a effect due to matter that allows you to differentiate those 2 orderings. And there is a current and fusion neutrino experiments are expected to determine the ordering. I bet you $100, but at the end of the decade we will know it. That my money is on this one, but we'll see. Okay. So what's important is the neutrino oscillation length. The neutrino oscillation length, so that's the distance to this first oscillation maxima, is given by this. Okay, so it's from a previous equation. And in useful quantities, is given by this relationship here. So this is something that you should have handy because it's useful scales. So that means that if I have a 1 GeV neutrino for 1 electron volt square, it goes about 2 kilometers distance, 2.5 kilometers. So if I want to think about the shortest oscillation length, so the distance that is closest to me, I have to pick the largest of the mass square differences. And if I do that, I end up that if I have a 10 GeV neutrino, the oscillation length is about 10,000 kilometers. That is roughly comparable to the diameter of the planet. If you have a 1 TeV neutrino, I get 1,000,000 kilometers, much larger than the planet. And if I pick a 1 PeV neutrino, that's 10 to the 9 kilometers. You can see this glows linearly with energy. And somewhere between this and this is this distance between the sun and the Earth. OK. Conclusions. Well, this implies that for neutrinos from other galaxies, we're actually in the regime of many oscillation lengths, right? So if I'm talking about 100 TeV neutrino, the oscillation length is ordered like the size of our solar system, and these are going actually in principle megaparsec scale. So we're in the third regime. That means that we are actually in the regime where the oscillation probabilities are averaged out. In the averaged out oscillation probability regime, there is no dependence on the energy between the flavor range of neutrinos. And that means that you can actually write the neutrino oscillation probabilities in this regime in the following way. So the transition probability from alpha to beta is given by the sum over the mass states of u alpha I square times u beta I square. So it only depends on the matrix elements that dictate the neutrino oscillations. Okay? There is no explicit L or E dependence. Are there any questions on this? Yes?
When you compute the oscillation length, you said that you bet like $100 when choosing one. Like, is that just like, is there a privileged way of doing this, or just at a specific case? Like, do you have a bias for that? Why would you bet $100 when choosing like the line before?
Oh,
Yeah,
this?
when choosing, like, why did you choose this one? Is there a specific reason?
So actually, my bet is stronger because I have a double bet on that bet, in that I said both that we will know by the end of the decade, and additionally that it will be this one. So it's a double statement. I say it for two reasons. First is that there is two experiment. There are two reasons why I think the ordering will be known. One is there's an experiment to be built in China called Juno that has at least 3 sigma sensitivity for the neutrino ordering. And additionally, atmospheric neutrino experiments like Super K, Antares, or Chemtrinets, and IceCube to some extent, are also sensitive to the neutrino ordering with their uprates. And those are supposed to get 5 sigma sensitivity by the end of the decade. So that's the first statement. The second statement is that there actually fits that aggregate data from multiple experiments. And even though there is no individual experiment that tells you this is the ordering, the data has a tendency towards neutrino normal ordering at somewhere around like the 2 sigma level. Okay, so it's not that significant, but that's why I'm going in that.
Thank you.
I should say that if the ordering is normal, it's a little unfortunate because neutrino experiments that look for neutrinos level beta decay that tend to find that neutrinos are Majorana in nature have a harder job determining the Majorana of neutrinos in this case and that case. Additionally, cosmology also will get to the neutrino ordering or masses faster in this case than in that case too. So it has implications beyond neutrino physics. Okay, good. Okay, so the conclusion is that for astrophysical neutrinos, we actually do not expect to see oscillation features. We expect to see these flavor transitions. Are there any questions on this? Because that's where I'm going to end this little review on neutrino oscillations. Yeah. Mike.
So you showed this to the 2 flavor case, but I assume this would be true for the 3 flavors of neutrinos, like
Yeah.
Whatever source we expect, whatever flavor of neutrinos being shot at us.
Yes. What I discuss here extends to the 3 flavor scenarios. This equation here is true for 3 flavors already. The equation I showed you above with the sine square and the sine square theta 2, that's actually specific for 2 flavors. This relationship works for 3 flavors.
Okay, thank you.
There is another interesting point here, which is the fact that, like I was mentioning earlier, neutrinos are, in principle, have a finite localization. So when you produce a neutrino, like from a pion decay, say like that, in reality, you are producing some kind of, let's say in space, some kind of neutrino wave packages like this. Okay. That corresponds to the 3 neutrino mass states that are superposed in that production region. So if these actual neutrino wave packages, as they travel through space, are actually going to separate themselves spatially because they actually go at different velocities. So here in the Earth, you actually could get something that looks like this. Well, then the neutrino state is actually completely separated. It's not clear if this actually happens because this depends on how tightly packed the initial neutrino states are. Okay, so the initial separation of the neutrino states is actually depends on the production conditions of this pion. So it depends on the how boosted this pion is, because that's actually going to flatten the pion wave function. It also depends on the environmental conditions of the pion. But in principle, under some scenarios of the pion wave package, the neutrinos will actually separate like this, and then you will actually get an incoherent summation of neutrinos. And so another way you can interpret this formula here is that you are actually emitting an incoherent sum of neutrinos I, weighted by the initial flavor, and then you are detecting them in a sort of incoherent way. So if you assume that neutrinos are totally decoherent, which is the scenario you get, the scenario I just mentioned, you actually get the same relationship. Okay, but at the time, we actually are not 100% sure if the neutrinos actually separate their wave packages or not. But in the end of the day, it doesn't matter for us, because it turns out that unless somebody figures out to have awesome energy resolution and spatial resolution, you can actually not distinguish the case where the wave packets are separated or where you just average out the oscillations. So that's, I think that's neat. Okay. Cool. Now let me switch back here to here. And now let's see if I scoop it up. Cool. So after that interlude, we can continue. And first I want to show you this picture here. It's nothing as good as data. So here there is an image from the CAMLAN experiment that's in Japan. CAMLAN is a reactor neutrino experiment that uses the flux of neutrinos from a collection of reactors in Japan. And so here they have actually measured the oscillation probability. This is the survival probability of electron neutrinos as a function of L over E. So just so you can see this wiggle. And you can see that this wiggle sort of flattens out. And this flattening is because of this finite resolution that I was talking to earlier. Okay. So now let me talk about high neutrino astrophysics and neutrino flavor composition. Maybe, wait. See if this, oh, yeah, back. Oh yeah, somebody had a question.
In the previous slide, what is the data?
Okay. Here. The data here are electron neutrinos detected by a reactor neutrino experiment in Japan called CAMLAN. It detects neutrinos through a process known as inverse beta decay. So it's essentially the number of neutrinos observed rescaled by the baseline expectation. Does that make sense? You're counting neutrinos at a given energy, and you know your typical distance from your reactors, and then you plot the number of neutrinos you get at a fixed energy as a function of the length. Does that make sense?
Kind of.
So you have, let me say this in another way. You have so how this plot is done is, so suppose that the CAMLAN experiment
we
is...
do not see what you writing.
Yeah, so the CAMLAN experiment says here, and it's in Japan. I'm going to approximate Japan by a square, okay? Okay, so, and then it has reactors, nuclear reactors. Okay, nuclear reactors are emitting a lot of electron and neutrinos, right, with some spectra. So there is some spectra of electron and neutrinos emitted by the reactor. Okay, so now there is an average distance of all of these reactors. Okay, so what I do in my detector is I make a plot of the energy of each of my neutrinos. And so I count every neutrino, and for every neutrino I can measure its energy. So that looks some kind of histogram. And what I do is that then I divide out by the average length, and I end up with this plot here.
Okay, thank you.
No problem. Okay. So let's talk about high neutrino flavor composition. So I just want to think about this in another way if the previous discussion wasn't maybe transparent for you. But you can think that neutrino oscillations is a lot like double slit experiments. When a double slit experiment, you actually have that the light goes through different paths, and then what we get is an interference pattern in light. The difference here is that we're going to have, instead of a light pattern, we're actually going to have flavor states, and those are actually going to go through two different trajectories at point and relative phase. And a relative phase, instead of making a pattern in light, it makes a pattern in flavor. Okay, that's an analogy phenomenon. Okay, what I was mentioning earlier is that, like in a normal interferometer, if something were to modify the interactions of my neutrino states as they go from the source to the production, then this modification will actually imprint a change in the flavor pattern that you see in this window. So this is one of the reasons that neutrinos are so powerful for beyond standard model physics. Some of the most precise measurements that we have in physics actually are interferometric measurements, right? So we're actually essentially measuring these sort of frequencies, but now in flavor. And I'm going to talk about examples of what those physics is later on. Okay, so this is a sort of cartoon of the flavor composition of these neutrino sources. The sources are unknown, and maybe they have a different name because this is, sources in optical light. But we typically talk about sources in three different categories. We talked about pion sources, and pion sources are such that they produce a pion. This pion, of course, decays like this, and then this muon subsequently decays like that. And so in a pion source, you end up with 2 muon neutrinos and 1 electron neutrino. So if we look at the relative amounts of electron, muon to tau neutrinos, we can label that as a 1 to 0 source, right? So no tau neutrinos and twice the number of muon neutrinos to electron neutrinos. If the pion decays in the region of high magnetic fields, that muon will synchrotron radiate before it decays, so it will lose energy. And it will lose energy before it actually decays into high energy neutrinos. And so in that case, this muon decay will happen at lower energies, no longer contributing to high energy neutrino emission, and you end up with only muon neutrinos. And so we're going to label that as a 0, 1, 0 source. You can also have production of neutrons. And if you have neutron decay, you produce only electron neutrinos. And so we label this as a 1, 0, 0 source. In a realistic source environment, we expect mostly a combination of these two processes, mostly dominated by this process here. But these are like prototypical, say, simplified cases. So the game is the following. So you have some initial flavor composition. It's unknown, but we think it's probably pion. And then there's going to be some flavor mixing. This is given by this equation, which we derive in the standard model case. I will show you how to derive it in an arbitrary case. And then there is some production at the source, which may be this pion scenario or muon damping scenario. And so you're going to get some flavor composition at the earth. And I'm going to, spoiler alert, tell you the answer for this. But in the standard scenarios, the flavor composition that we expect from astrophysical neutrinos are close to equal flavors, with possibly small deviations from that. But it's possible that that's not what happens in nature, and something really weird happens. And so that may be a statement of new physics. So we like to talk about the flavor triangle in talking about flavor high energy neutrinos. And this tells you the proportions of different neutrinos at Earth. And so let me spend a second how to read it. Sorry, these numbers are really tight, so it's very confusing to read this, but 0 is here, 1 is here. So this is the fraction of electrons at Earth. This is the fraction of muon at Earth. This is the fraction of tau at Earth. And so if you are here in the top, that means you are 100% muon neutrino, you are 0% tau neutrino, and also 0% electron neutrino. If you are in this corner here, then you are 0% muon neutrino, 0% tau neutrino, and 100% electron neutrino. And if you are here, that means you're 100% tau neutrino and 0 of the others. And if you're somewhere in the middle, for example here, then you read horizontally for the muon fraction, in this inclination for the electron fraction, and in this inclination for the tau fraction. So this is about 1/3, 1/3, 1/3. Is this clear for everybody? Please tell me, because I'm going to show you like 20 plots like this, so if this doesn't make sense, it will be confusing. Good. So you can think about what's the allowed regions of flavor space if you assume that neutrino oscillations have to follow a unitary evolution. That means that you cannot lose neutrinos as they travel from the source to us. So that's the statement of unitarity. And it turns out that unitarity requires already some allowed regions. So for example, if I start with an electron neutrino content at the source, you can only be inside of this red region. If not, you actually violate the unitarity. If you are initially a mu neutrino beam, you can only be inside of this region here. Again, it's a unitarity statement. And if you're in a pion beam like this, you can only be inside of this blue region. This statement only requires me to say that the number of neutrinos is preserved. That's it. Okay? If neutrinos decay or do something else like that, then it's no longer true. But we can actually do better because we actually know the neutrino oscillation parameters. So this is sort of the same way of looking at it, but now I have actually done like a distribution of points. So suppose that I can produce an arbitrary matrix, okay, according to some random matrix, and I want to just randomly choose a matrix, a 3 by 3 matrix that represents the flavor composition. This is then the distribution of possible points weighted by that matrix. So most random choices actually tend to give you something close to the center, if you pick the mixing angles to be just arbitrarily given. Okay, so how do you compute the probability of transition from a flavor alpha to a flavor beta in a general way? Yes. 2 slides. This one here. So her question was that, yes, just for the recording, why is it that there is a constraint in these regions? Essentially, imagine that you have two cases, right? So imagine there are only 2 flavors. Okay, so if you start with let me see how do I say this. Okay, so this point here, okay, it allows you to have 50% of the neutrinos be converted. So I start with 100% electron neutrinos. Okay, this represents that at most you have 50% of them have become mu neutrinos. Okay. This here represents that at most 50% of them have become tau neutrinos. Okay. But I can never have a situation where more than 50% become, like, for example, I cannot have a situation where on 80% of my neutrinos become of a different flavor. It's because the sum of the mixing elements have to add up to 1. In that, if I have it here, what I'm saying. If I have a matrix that relates neutrino mixing, so this is my mixing matrix U. So I have, this is U, E1, U, E2, U, E3. Then you always have to have, if this matrix is unitary, you have to have that the sum of U alpha I squared has to be up to 1. And so has the columns, okay? So now, what you do is you start with an initial flavor, right? So you say like your initial flavor composition is just electron neutrino only, right? So this condition here does not allow you to put any arbitrary fraction in the other states. And when you actually do the math, you get that you cannot have the other one. So it just comes from this math. Oh yeah, we'll talk about that in a minute. We haven't talked about that, yes. We'll talk about the ice cube version in a minute. Good. Okay, so, oops, ooh, wow, that was fast. What I want, okay. So how do I compute the transition probability in an arbitrary configuration? So what you have to do is you have to do Hamiltonian, and you diagonalize your Hamiltonian like this, right? So this is, you can always do this. So this is the eigenvalues of the Hamiltonian. So as long as these eigenvalues here tell you the difference between these eigenstates tell you the oscillation length, right? So as long as the difference of this oscillation length is smaller than the distance from the sources, the relationship for average out sources still holds, which means that the oscillation probability is still given by this equation. But now, instead of having the PMNS matrix as the elements here, you have whatever actually diagonalizes your Hamiltonian here. Okay? So that's how you get it in arbitrary fashion. So what you can do is figure out where you end up if you now know the PMNS matrix elements. So here I have different colors represent the different initial beams. So here I have pion, neutron, muon damped, and I put some taus and Arguelles for completeness. And so here is again the fractions, and each of these blobs allows you to tell you the region that's allowed. So why are these regions not a point? So if I were to know the PMNS matrix, if I were to know the oscillation parameters with arbitrary precision, then every of these points should be a single dot. Okay? The fact that I have an error on those parameters is what actually gives these regions some width. And this is actually using constraints now for several years ago. And what you can see is that you are only allowed to be essentially in this region and in these regions. And if you take linear combinations of these contributions, they actually allow you to be only in this center part here. That means that if you end up in any of the white space here, you actually must have found new physics. There is no way you can do that. So this is one of the reasons that looking at neutrino flavor is one of the most powerful proofs for new physics, because in this statement, I only required unitarity in the neutrino evolution and the current knowledge of the neutrino mixing. It's independent on essentially the neutrino spectrum and whatnot. Okay. So how well do we know that matrix? Well, it depends if you assume unitarity or not unitarity. Here is the PMNS matrix elements measurements shown in two different ways. So every row corresponds to a different flavor row. This is electron 1, electron 2. So what does this mean? This is the fraction of, or the square of this is the fraction of electron neutrino in the first mass state. This, the square of this is the fraction of electron neutrino in the second mass state. And this is the fraction of electron neutrino in the third mass state, and so on and so forth. And so you can see that the electron row is very well measured. Comes from a combination of reactor accelerator experiments. The muon row is measured to some extent, and then the tau row is also measured to a comparable extent. And here I show you two different lines. So the red line, I want you to focus on the red line, in the dashed line first. So the dashed line assumes unitarity, which means that if you assume unitarity, you only need to measure actually 4 of the quadrants, right? Because if I measure this, and that, I can compute this one by just subtracting 1 minus that, and I'm done, right? So if you assume unitarity, you only need to measure this sector to obtain, or this tree to obtain the whole matrix. However, if you assume no unitarity in the neutrino evolution, what does that imply? It implies that, for example, you could have additional neutrino states. This is not such a wild thing to believe, because we know that neutrino masses exist. That means that at least some new neutrino state must exist to provide those masses. The question is what is mass and what not. And so now I want you to take a look into the blue line. And so the blue line is the knowledge of our neutrino oscillation parameters, where you now remove the condition that there are only 3 neutrinos that exist in nature. And so you can see that now the tau row is actually quite wide compared to the other rows. And the reason is that it's extremely difficult to measure tau neutrinos. We only have measured a handful of tau neutrinos ever. Okay? So that's the statement. So you can look at the effect of that. So this butterfly in blue is the allow flavor region if you assume unitarity. And this, let's say, square in orange is the region if you allow for non-unitarity. it's still, it's a very well-defined region on parameter space. I'm not going to talk about this tetrahedron because it's kind of complicated, but you can talk about that later. Okay. So you can modify the neutrino flavor ratio by adding new physics. For example, in this paper by Mauricio Samanda and collaborators, they talk about neutrino decay. So we know that there are 3 neutrino mass states. Assume, for example, that we are in a normal ordering, which means that only the lightest of the neutrino mass state is nu1. So this is given by these states. So your mass spectra looks something like, like that. This is m squared. Okay. So if you allow for the neutrinos, neutrino 2 and neutrino 3 to decay, they can decay in the only stable neutrino you will get is nu1 in this scenario. And that means that what you should observe at Earth is the flavor composition of your nu1 states. And that's given by this one here. Okay? So now if I measure the flavor composition of the neutrinos, and I have some ice cube bands here, I can start actually ruling out the stability of the neutrinos just by looking at these conditions. Of course, this depends on the ordering and some other assumptions. So you can see how this compares to other constraints. So this is what you can do for, this is the lifetime of the neutrinos in seconds. This is constraints from atmospheric neutrino experiments, solar neutrino experiments, and this is what more or less we can get with ice cube currently, and this is what we could get eventually with better ice cube. And this was done before the galaxy was in a neutrino, so it's actually good. Okay. Cool. Questions on this? Okay. Another thing that's kind of cute is that you can also have non-standard interactions in the planet. That means that when neutrinos are actually going to the Earth, they could have interactions that are no longer flavored diagonal, and that's going to modify the allow flavor transitions. So those effects tend to be small in most of the cases, especially if they are in the pion-dominated scenarios. But if you have some other exotic scenario, for example, if you're in the muon-damped scenario, you could actually get large deviations. And in this muon-damped scenario, what that means is that you're actually constraining new physics that relates to neutrino interactions. Okay, I'm going to talk about this a little bit more later, so I'm going to skip this for the time being. But this is a nice way of thinking about this. So here is again this triangle. So remember always electron flavor, muon flavor, and tau flavor in all of this. And this shows you the different ways in which you can modify the neutrino flavor depending on where you put your effects. So for example, here, these are source effects. So for example, if there is a non-standard interaction, that's something that's not predicted in the standard model, at the source, you can modify it within this boundary here. If you have production of heavy neutrinos, so this is this new S, you can have something like that in now at Earth. You can also have effects at detection. So this is what I was telling you earlier. For example, if there is some new interaction between neutrinos and quarks that is not previously known, that will also modify the flavor of neutrinos that you see. And so this is separated in 2 categories: if the interactions happen in my detector, or if they happen somewhere in the path from the surface of the Earth to my detector. And then you can have effects that are due to the or happen in the travel of the neutrino from their sources to us. And so there are many things that we have talked about. For example, if you have some dark matter neutrino interaction, I'll talk about that a bit later. Some effective operators that parameterize interactions between neutrinos and vacuum, neutrino decay, pseudo-direct neutrinos, I'll talk about that later, or maybe the presence of additional neutrino states. And they all will do weird things in your flavor triangle. And remember that what I was trying to emphasize earlier is that the standard model prediction on this is actually quite robust. But the physics we're able to prove is quite varied. Okay. So if we measure the, if we have that flavor contribution, we can actually now predict observables in detectors like ice cube. So for example, you can look at the ratio of track to showers, right? Remember that tracks are produced predominantly by muon neutrinos, and showers are produced by essentially all the other types. So the track to flavor ratio is a proxy for the flavor of artificial neutrinos. And here you have prediction from different cases. So if you have pion processes, you end up somewhere here, a little less than 1/3. This is the damp muon scenario. And then this is the neutron decay mode where you produce typically a lower abundance of tracks to showers. Okay, so this gives you a sense that measuring one way of measuring or accessing the flavor composition of neutrinos is by looking at the relative contributions of track to showers. We actually have better ways to doing it, but hopefully it gives you an intuition. So that actually can be improved by what I call ternary classifications, which is trying to find tau neutrinos. One of my students actually wrote this poem, which we put in our paper some years ago, which he was really a very tau enthusiastic student, so it's very cute. So tau neutrinos, they're difficult, but they're very powerful. So in the Earth, when we're talking about backgrounds, remember that I was saying that most of the neutrinos produced in the atmosphere actually come from pion decay. That means that there is a very small component from neutrino production due to heavy mesons that actually come from D mesons, but that's a very, very small contribution. Which means that if you find tau neutrinos in your detector, there is a very, very good chance that those actually are astrophysical in nature. There is some caveats to that statement that we unveiled quite recently. And this actually is something that surprises people when I tell them this. Maybe you will be surprised, maybe not. But actually, when neutrinos travel through the Earth at very high energies, the capacity to produce a real top quark is actually about 10% of the time that the neutrino will actually make a top. And that top will decay into a B plus a W. This is very weird because we never think about neutrinos making top quarks, but they do, which is sort of like LHC exclusive thing. And we can also have production of Ws through this sort of photon exchange diagram here. And in any case, the decay of these Ws that are produced either by top quark production or by real W production through glass show or other processes produces actually 1/3 of the time tau neutrinos. So it's possible to have, in reality, no tau neutrinos arriving at Earth, and still produce tau neutrinos as the neutrinos travel through the planet because of this top production and W process that appear there. I noticed that in this cartoon I tried to put the Andes by putting some llamas here. Okay. So taus are very difficult to see. They have been seen in 2 terrestrial experiments. One of them is Donut, and then one is Opera. I believe this happened at Fermilab, and this was in Europe, operating on CERN beam. And the way you see a tau is the following way. So let's look at this Opera case. You have a neutrino that comes in, it interacts, particle comes out, and a tau is produced. That tau, remember the tau lifetime is about 10 to the minus 13 seconds. So it only goes to a very small distance before it decays. So it goes in a little bit, it decays, and then neutrino comes off, and then you get this particle that comes off. So you see this little kink that appears in your distribution. So seeing this kink is very, very difficult. That's one of the reasons that we have only seen a handful of taus essentially ever. The good news is that when you have a high energy neutrino beam, such as neutrino telescopes, the tau actually travels quite long distances. So if you have a 1 PeV tau, that's going to go 50 meters in ice or water. Okay? So this tiny, tiny kink, this is done for an order GeV neutrino beam, becomes 50 meters. Okay. So how do we obtain the flavor composition of neutrinos? Well, we have a ternary classification system where we classify neutrinos in 3 morphologies. One of them is tracks, these long positions of light. Those are predominantly produced by atmospheric muons, muon neutrinos, and sometimes tau neutrinos when the tau decays to a muon, which happens about 70% of the time. Then you have cascades. Those are produced by neutral-coulomb interactions, as well as charge-coulomb interactions from electron neutrinos. We talked about this earlier, so I'm not going to dwell much. And then we have these double cascades, right? So double cascades, we typically talk about them when the separation is more than 10 meters. And those are produced by the first light deposition is produced when the tau hits the nucleon and emits energy. And there is a second deposition when the tau decays. Okay? And so by classifying event into these three morphological categories, we can extract the relative amount of muon, electron, and tau neutrinos. Okay? So in principle, this is it's a sufficiently constrained problem. So there are actually two tau neutrino candidates observed in the last Hesse analysis. One of them is Big Bird, and then one we call Double Double. So the energy of these two events is, one of them is Big Bird, so it's about 2 PeVs, and the other one is about, I believe, 70 TeVs. Okay? And the length given here, it's on the orders of 20, like I think it's 14 meters or 17. We'll see it in the next slides. Another way that we can differentiate double cascades to other, so the concern here is tracks that have an unusual energy reposition. Remember that muons, when they travel through the ice or the water, they lose energy stochastically. So it is possible that you have a muon that suddenly decides to lose a lot of energy, and then be very shy and quiet, and then loses a lot of energy. That's very bad. So that's a problem. So there is actually one thing that we could use here, which is the difference or the energy asymmetry, so the relative energy difference between the first and second cascades to the total energy deposited in the event, and it has some separating power with respect to backgrounds. So the main backgrounds here, you have single cascades in true, double cascades and tracks, which is essentially muons. And you can see that our two events, event number 2 is in a region where the energy asymmetry, so the relative difference between the energy of the showers, actually supports a single cascade hypothesis a little more than a double cascade hypothesis. However, the energy difference in the second event here actually supports more a double cascade hypothesis than a single cascade hypothesis. So it's not only that you want two separated energy losses, you want them to have the right proportions of energies for it to be compatible with a tau to claim these are double cascades. This is Big Bird. This one I don't think is a tau, just so disclosure. So here is the events. This is the main display, of course, and these little panels around it show you the time series of photons observed in nearby sensors close to the interaction points. And so you can see that there are two lines here. There is the single cascade hypothesis and double cascade hypothesis. They're very similar, sometimes a little different, but nothing really picks your eye. And then there is this one, which is our first astrophysical tau neutrino event. We call it Double Double. It's 90 TeVs, 70 meter separation. And you can see here, this is the event. This is the most likely first point of production and decay. You cannot see that by eye in the event display, but I want you to look into is to look into the time series of light of the nearby sensors close to the interaction point. And what you can see is that these nearby sensors have actually two light emissions. There's a first light emission here, then it goes down and up, it goes again here, and this one's here. Okay? So this is what gives us confidence that this is really a double bank event. And the confidence of this being a tau is actually quite high, above 2 sigma. So you will ask yourself, this is interesting. Have you seen more of this because all of this machine learning going on these days? The answer is yes, but we're still working on it. So we'll know later this year. OK. So with that, you can measure the flavor composition of astrophysical neutrinos using this ternary morphology. This was published last year. It was on the cover of APJC. And so you can see it here. Again, this is the electron fraction, muon fraction, and tau fraction. And the numbers are inclined in the direction in which you read the fractions. The butterfly shows you the standard model prediction for essentially any combination of scenarios with different benchmark points highlighted. And then our most likely solution is this one here. Very close to standard solution. with the 68 and 95% contours shown here. So these contours are a little sad because most of the triangle is allowed in these measurements. We disfavored essentially 100% electron neutrinos and 100% mu neutrinos are ruled out. There's another way in which you can try to see the double bands. It's known as a double pulse technique. And that implies that instead of trying to reconstruct the whole events, maybe you could look at individual PMTs and see if an individual PMT has a double pulse waveform. So how this looks is like you can have a normal, for example, electron-neutrino interaction happens nearby a dome, it emits light, you see that. But if you have a tau neutrino, maybe it goes only a little bit, but this distance may be enough that it produces two light depositions. So what you look at in your sensors, this is voltage, and this is time, nanoseconds. You can see that for a single cascade scenario, you should get something like that. But for a double cascade scenario, you can look for this. So one thing that's nice about this technique is that it has a lower threshold than trying to reconstruct the whole event, where we actually try to infer the distance. And so it's complementary. Okay, so our double pulse algorithm essentially tries to find these three edges. So we find a first rising edge, a trailing second edge, and this, and we adjust the width and steepness to try to reduce backgrounds. Okay, let's skip this. So it actually found a handful of events. So this was one of them. It's one in 2014. So the p-value for this beta tau is not particularly high. This one here. And I think this one is the second one being the double-double I was telling you earlier. Cool. OK, are there any questions on these flavor measurements before I move on into particle physics and other topics? Wait, we started at noon, right? 10 to noon. OK. That's not good. OK, so we have maybe, let's say, 30 minutes. Questions on this? OK. So I want to tell you, a little of what more can we do here. And I'm going to show you a panoramic vision. So this diagram, it's made for ice cube, but it's true for all neutrino telescopes. Essentially, neutrino telescopes are multipurpose observatories. And we can do astrophysics, and we can do neutrino physics, earth sciences, dark matter, Bessel model, and searching for fundamental symmetries. And I want to give you a sense of how we accomplish these different things. So one thing that we do is, of course, studying the cosmic ray flux. We characterize atmospheric neutrinos. We try to find production of D mesons in the atmosphere. One thing that we are trying to measure is the production of prompt neutrinos. That is, neutrinos that come from D meson decays. This is important because it's something that cannot be measured so far directly in collider experiments. And this is some of our latest measurements. As a function of the energy, these are different models for the contribution of neutrinos from D meson decays. These are our current upper limits. So we're getting to the region of interest, but we are not quite there. So we haven't actually seen these neutrinos. Another neutrinos is what Orlando was asking me yesterday, which is neutrinos looking at the sun, right? So you have the sun, and they're cosmic rays, and they're hitting the sun, and they must produce neutrinos somehow because you have PP collisions. So how close are we seeing sun and hydrogen neutrinos? So we call them sometimes solar atmospheric neutrinos, but they have different names. So how are these neutrinos produced? Essentially, what happens is cosmic rays hit the solar atmosphere. This is the density of the sun as a function of the radius to the solar center. They start mostly interacting in this outer layer, and then there is a long, like very rarefied space where the muons that are producing these, let's say, PP interactions, then that followed by pion and then decay. And then once these muons decay, the neutrinos go into the sun. And then what you have to do is solve what's known as the neutrino transport problem. So you have to track these neutrinos throughout. And the reason this is not trivial is because you have to take into account that the neutrinos in the sun, if they have high energy, will actually interact in the sun, and they will actually also oscillate in the sun, because now the size of it is not large. So what you do is you have to solve this quantum Boltzmann equation, where you have to take into account both simultaneous neutrino oscillations and interactions, which you can solve with one of these codes here. So once you compute the production of neutrinos at different distances, you're going to get different impact parameters and neutrino flux. This is shown scaled by E cube, and you can see that you get this oscillation behavior. Here, the different panels correspond to different flavors. It's electron neutrino, mu neutrino, and tau neutrinos. And then what you have to do is you have to take into account the fact that the Earth and the Sun distance is changing throughout the year, so you have to average out over that change. And you end up with plots like this that show you the expected neutrino at each of the flavors, for neutrinos and anterneutrinos separated, once you get to the Earth. So this spectra is approximately an E⁻³ spectra, and actually at high energies, somewhere around tens of TeVs, you can still see oscillations, and at lower energies, I'm going to see that. So we expect to see that hopefully pretty soon. So in the case of IceCube, we expect to see order a handful of events per year. And what I can tell you is that our next generation analysis, that I hope will get unblinded, that means we'll look at the data, later this year, we are within a factor of 2 from actually seeing this flux. So maybe we get lucky and we see it. Another thing that this was discussed some days ago is the search for dark matter. Of course, these neutrinos produced in the atmosphere are actually a background for searches for WIMP annihilation in the sun. So the idea here, I will only mention this briefly because I know it was discussed earlier. The idea is that WIMPs can capture in the sun, and they can then annihilate, producing neutrinos. And so this actually is one of a background that is not irreducible, because the energy distribution of neutrinos produced in cosmic ray collisions and the ones produced from dark matter annihilation is actually going to be distinct. So in principle, you could differentiate them, but it does put some limit into how far you can see easily into the sun. Okay. You can also have acceleration of protons in solar flares. Solar flares has magnetic fields, so you can accelerate protons to GeVs of energy. And so that's very difficult. So I have actually been very selective with my event displays, and I have shown you only high energy events that look like this. It's beautiful, many hits happened. However, many neutrinos in IceCube do not look like that. Most of our neutrinos are actually low energy, and this is how a GeV neutrino looks in IceCube, right? So it's only a handful of hits. So it's very difficult to actually reconstruct these neutrinos, figure out this direction. If I were to tell you if this is a track, a cascade, and what's the direction, you have a hard time figuring that out. Kamiokande has a better directionality, but it's too small. Okay. So his question was about Kamiokande capacity to do this. Yes, the resolution of Kamiokande is better, but it's just too small. But the thing here that saves you is that you know the solar flare timing when it happens, so you can do a coincidence search in time, right? So it's something that we're looking into. I think that this is an interesting thing. I was mentioning this to Orlando, we were talking yesterday, and it's the fact that the sun is doing weird things in gamma rays. So this is the energy, okay, of gammas. This is the flux, okay, in times energy. And this here, this thing that says SSG91 is a calculation of production of gamma rays from pion decay in the solar atmosphere or the solar outer regions. This is actually the data from Fermi. You can see that it's off by a factor of more than 10. And there was a recent paper by these authors here, now a handful of years ago, that actually measured the flux of gamma rays produced in the sun from pion decay. Well, we don't know if it's from pion decay, but we speculate it's from pion decay. And what they found is that somewhere around like 40 GeVs, there is this dip in the gamma ray spectrum in the sun. And so far, this dip is still unexplained. We do not know why it's there. But certainly statistically significant. And so the idea was like, okay, maybe we have to keep measuring, see what's going on maybe over here, and see what happens. And the good news is that we have now, as of I think it was last year, seen the quiet sun in the hog experiment. So the hog experiment is in Mexico, and is constructed of these water tanks, about 300 water tanks. So it's a water Cherenkov detector. And they have actually been able to observe the sunny high energy gamma rays. So here is that data I was telling you earlier. This is the Fermi measurements with this dip here. And then the measurements from Hawk are these points here, where they measure it both in the solar minima activity and the solar maximum. And you can see that there is a distinct difference between these two times. So this is interesting because this is telling you that something non-trivial is happening with these protons. It's possible that the protons are getting trapped, and they're increasing the chances for them to interact, making pions. So my hope is that something similar will happen with the neutrinos, and our latest analysis includes more solar minima data, so maybe we'll find some sunny neutrinos very, very soon. And this is just for record how their data looks from Hawk. So this is some position in the recent paper. Another thing that's I think cool is that you can measure the high energy neutrino interactions. And so you can measure the total neutrino cross section as a function of energy. So this is the current measurement. This is some calculations for it. And you can also measure the average inelasticity of the neutrino cross section as a function of the neutrino energy. Here shown for neutrinos and antineutrinos separated, and then average we would expect for the fluxes. So far it seems to agree. But what's up ahead of us? So here, this is the neutrino energy. This is this sort of measurements. These are essentially these ones here. And we have measured the neutrino cross sections now all the way to hundreds of TeVs, but we expect to measure them at higher energies with the IceCube Gen 2. So a bunch of different things that happen. For example, you have this sort of color condensation where the gluons inside of the quark very deep between them, sort of shadow between the anode and the gluon structure fraction stops growing. You have contribution from large external dimensions or spirals. And I want you to compare these to center of mass energies of accelerator experiments. Here is the Tevatron, the LHC energy. So we hope that in IceCube Gen 2, or next generation neutrino observatories, we're going to get to these energies here. But so far, everything looks standard model-like. We announced, I think this was in 2020 or 2021, the observation of the first Glasgow event. So this is actually a real W that's produced in a neutrino electron or electron antineutrino interaction. Remember, this is a new EVAR, interacts with an electron, makes a real W. And in particular, this W actually decays hadronically, so this is not quite a real decay process. This was a very difficult analysis because this interaction point was not contained within the detector instrumental volume. You can see this from the top view. So the interaction point was actually on the side of the detector. This event, we call it hydrangea. Hydrangea is a flower. And the most likely energy of this event is very close to 6.4 PeV, which, as you remember from lecture maybe 1 or 2, is the energy that you require for a neutrino to make a W on shell. So how do we know that this is really a W? Well, and not some background. So your signal is this hadronic interaction, and your background could be maybe electromagnetic showers or muons from pions. And the reason is that the interaction happens, and there is a hadronic shower that starts a hadronic process. And this hadronic shower produces pions, and those pions decay into muons. And muons are actually going to move ahead of the main Cherenkov front. And so this blue line is the emission of the cascade, the light emission of the cascade, and these red rings are actually the emission of Cherenkov light from the muons produced from these cascades. And so what we see in our data, this is the event coming in, and what we look at is the first DOMs that are hit in our detector. And when you can see those sensors that are close by, you can see here this red line. This is the time that we expect the main Cherenkov front to hit our detectors. And these hits are actually arriving before the main Cherenkov-Proudhon hits. And the only way this is possible if there are these muons that are coming before the main fronts. And that's how we know that not only this event has the right energy to be a Glasgow resonance, we know that this actually has a hadronic shower included in it because of the presence of these leading muons. So this was published, I think, in Nature a couple of years ago. I think I have like 10 minutes at most, right? Or minus 10. Okay, so I'm going to do an executive maneuvers because I do want to talk about the future. So I'm going to skip this dark matter discussion for the time being. You can ask Dia later. Let's see. I'm going to skip to this. So I think this is maybe one of the most exciting things that are going on, and I don't want to not talk about this because I think this is really cool. So remember that the neutrino oscillations length depends on energy divided by mass core difference. And so we have measured neutrino oscillations in the Earth, but now you can actually see these extra galactic sources or extraterrestrial sources. And so the question is if you could see oscillations now at these sort of length scales. And this is the formula that you get in general if you do not average over the oscillation length. Remember, I showed you this in a version where this was out, right? So suppose now that your oscillation length is comparable to your oscillation scale. You get this equation here. Okay. So one thing that you can have is something known as a pseudo-Dirac neutrino scenario. And this is a scenario where the neutrino masses are coming from some like Dirac-like mechanism, but there is a small correction that comes from essentially God scale physics. And that small correction essentially produces a small difference between the normal neutrinos and some new neutrinos that are responsible for the neutrino masses, known as sterile neutrinos, or right-handed neutrinos. And what happens is that now you can have oscillations between your normal neutrinos and these invisible neutrino types. And this can be seen here for this very, very tiny mass core difference as a function of energy. And you can see here oscillations between, for example, mu neutrino to this invisible flavor. And so the effect that you're looking here is the disappearance of neutrinos. And this theory is quite old. It's like classic neutrino mass theories from the 80s. The problem is, how do I look at this small mass core difference, right? There is no way you can do this kinematically, but you can try to do it with neutrino oscillations. So one thing that my postdoc at my student Chiara worked on is trying to figure out what we could do with IceCube and IceCube Gen 2. So what you can see here is the sensitivity that we have to these sort of models measured by this likelihood difference for IceCube and IceCube Gen 2 as a function of this mass core difference for different sources. And so the idea is that you will look at different objects and you will look for this appearance at the same ratio of L over E. So this is analogous to what we were talking earlier with Japan, looking at all of these different reactors, and then when you put everything together, you see these beautiful oscillation waves. And so our hope is that with our first sources, we will see first hints of this, but this analysis is pending. Okay, I'm going to skip this anomaly discussion because we have no time. So we're going to have an IceCube upgrade that is funded and will be started in 2025. This implies 7 new strings with 100 DOMs in each of them, though these DOMs are better than our current sensors. And they're going to install inside the innermost part of our detector. And the important part of this is that they are not only going to install DOMs, but we're also going to install calibration devices. So that's going to better understand the ice properties, which will improve flavor identification. So how does this look? This is our current sensitivity for a 4 GB neutrino. It's kind of sad, but now with the upgrade, it's going to be great. Okay. Then sometime, we hope at the end of this decade, we're actually going to deploy what we call IceCube second generation, which is going to be a 10 times larger volume part of IceCube that's going to use sensors that not only have a single PMT, but have multiple VMTs in them. So here, this red box is IceCube, and this blue region is going to be IceCube Gen 2. And just so you know, this little cylinder here is the upgrade in a couple of years. Okay. At the same time, in Europe, KM2Net is being installed. It has two sub-detectors, Orca and Arca, Orca by France and Arca by Italy. And they are actually designed for different purposes. So Arca is going to focus on TeV neutrino astronomy, and Orca is going to try to measure the neutrino mass ordering, which is what I was talking earlier about this bet. So they're going to use this detector to have many PMTs on them, so that allows for light to be seen in many directions and increase photon efficiencies. And you can see the spacing here. This is already under construction. About 15% of these detectors are already in the water. So in a couple of years, hopefully, it will be completed. They actually already seen atmospheric neutrinos for the first time. This is a function of the cosine of the zenith angle. And you can see this is their first atmospheric neutrino observations in KM2Net. In Russia, there is also another detector being constructed, almost completed. In fact, it's been a little of a radio silence situation, but this summer conferences, we hope to know the status of Baikal. And I think I will not go into bet any money, but they should be very close to seeing astrophysical neutrinos probably this year. And this is how the detector looks. It's a set of clusters that will be deployed in Lake Baikal in Russia. Okay, so this is one of their first data sets that they showed us a couple of years ago. This is also a kilometer scale neutrino detector. Then there is P1. This is a new idea that's going to be deployed off the Canadian shores of Vancouver, and it uses underwater facilities of the Canadian Oceanography Network to deploy KM2Net light detectors, and this is something that's currently under development. And then finally, there is Trident, which is a new idea to deploy a Chinese neutrino telescope, similar devices as the neutrino telescopes, but this one is actually 7.5 cubic kilometers, so the size of the Arguelles 2, and is to be deployed off the coast of the South China Sea. Okay, so the future is bright in neutrinos. We hope to have a neutrino network of multiple neutrino experiments over the next decade with a good coverage of the whole neutrino sky. And there is an additional neutrino detection mode, which is through radio, and that actually is studied in neutrinos in the EeV energy range. And that works by the fact that when you have a very high energy neutrino, in this shower, you have radio emission. So that's actually being also developed, and there is already an experiment called ANITA that already operating, and ARA that also operated. So this is a picture of ANITA. This is how these radio antennas work. So the idea is that these radio antennas are surveying the Antarctic glacier, and are looking for this radio emission from neutrinos. So far, no conclusive observation of neutrinos have been seen by this technology, but it's very promising. I have another idea which I like, which is the fact that you can also use mountains to detect neutrinos. So the idea here is you have a neutrino here, comes on, hits a mountain, it makes a tau. The tau comes out, it makes a shower, and you have detectors here. This is actually done in Auger for detecting neutrinos, but so far has put only upper limits. But one problem here is that geometry is geometrical acceptance is a key for the neutrino detection. So what you actually would like to have is something like this, where you have your mountain like that, and your array like here, and then all of your neutrinos are coming like that. But this is not very practical. Okay? But what you can do is you can look for places where you have this sort of like wall-like geometry. And there are actually 3 places in the world where you can actually do this. One is here, nearby here, in the Colca Valley in Peru, where you have more or less 10-kilometer separation between the mountains and about approximately 5 kilometers deep in the mountain. And our idea is to deploy sensors in one side of the mountain in sort of a vertical slope to look for neutrinos coming from the other ends. So what we're trying to look for is essentially light that comes from the opposite wall of the mountain. And this is very neat. And we expect to have about 20 neutrinos in 3 years, and we are helping some of that simulations. And so here is what we were actually last year looking for a place to put this. This is near a town called Tapai and a village called Cabanaconde in the Colca Valley. This image doesn't make any justice to this valley. This is actually several kilometers deep in height. And this is where we want to put our prototype detector, which are actually, some of these are going to be plastic scintillator panels, which we are building in my lab at Harvard. And my hope was to deploy it in this summer, but we are delayed, so maybe we'll do it in the winter. OK, so I want to conclude with this. This is how we have measured the neutrinos in the Earth as a function of energy and distance. All of these neutrino experiments have happened. But now we're measuring neutrinos, from like super high energies and super long distances. And the question is, what will happen? The answer is, we do not know. But, the future is quite bright. Here you have seen a timeline of our evolution of our fields. This is in years. Here you see the volume of neutrinos that we have to detect neutrinos. So this is ice cube right now, about 1 cubic kilometers. Somewhere in 2025, we expect GBD and ChemTreeNet to start operating, having a total neutrino telescope volume of about 7 cubic kilometers. In the 2030s, we expect to have ice cube Gen 2 operating, P1 in Cana and then Tambo, maybe in Peru, as well as the Chinese observatory, which is the size of ice cube Gen 2. So we're going to be order of 10 more effective volume. And at the same time, terrestrial experiments are improving the measurements of neutrino oscillation parameters, so we can really nail down the predicted neutrino flavor regions. So it's kind of hard to see in this plot, but this green balloon is the current flavor prediction for electron neutrino-like beams. And you see behind this white region here, that's the prediction. That's how well we will know the flavor composition once we make these measurements by doing our experiments. And this is our current flavor composition, more or less. This is what we expect to be somewhere in 2040. So it's only 18 years from now. OK, with that, thank you very much. As a picture of my group. So we collaborated in many of these slides. And thank you for your time.
Thank you for the lecture. How can IceCube probe whether neutrinos are Majorana or Dirac particles?
The short answer is we cannot. But if we figure out a way to do it, it would be really cool. I don't think there is a way. I don't think there is a way that we can figure it out that I know. Yeah, not that I know. Sorry.
And what is the range in the energy of the neutrinos that P1 will try to see?
Yeah, that's a really great question. So the P1 and Baikal have a different philosophy. So if you see these diagrams here, these detectors operate by cluster, right? And so you are making a choice here, which is the following choice. IceCube is a volume detector, right? There is no gaps in it, which is very good for things like starting events or cascade reconstructions. But if you only care about muon neutrinos, okay, then you do not need to contain the whole muon, because that's not very useful, right? You measure the energy losses. So the idea here is that instead of putting your detectors like in a volumetric fashion, you put them in these clusters. And remember that a high energy muon can easily go tens of kilometers, right? So you see a part of the muon here, and then it vanishes, and you see it over there. So there are some more backgrounds, but the energy range should be very comparable. But this is actually essentially optimized muon neutrino telescope. Okay? The same is true for Baikal, which was in maybe the previous slide. These are actually optimized for muon neutrino. And the reason is that we always thought that you could only do neutrino astronomy with muons. But now, with the new galactic plane results, we now know we can also do it with cascades. So things are a little in the flow. One thing that's nice about the water detectors is that in water, unlike ice, you can actually redeploy your strings. So if you can put them like that, and if you don't like them, you can move them around and put them in a different way. So you could decide that first, and this goes back to your question, it's like, what sets my typical neutrino energy? It's my spacing between my sensors. Okay, so if you want to optimize for, let's say, TeV, 100 TeV neutrinos for muon neutrino type, you can put some distance like that. and then you say, no, I want to look at the galactic plane in cascades, you have to reconfigure them in a tighter range.
Thank you.
More questions?
There's a question here, Rolando.
About the low energy events,
Oh, yeah.
can you comment on the reconstruction for that?
Yeah, okay. So the low energy events, we have a specialized detector called Deep Core. I'm going to use these 2 slides to talk about them. So Deep Core, I didn't talk about Deep Core, but it's these green strings here. They are optimized to reconstruct neutrinos below 100 GeVs. The way we measure the energy in Deep Core, because when you have a sub 100 GeV muon, like we talked, I think, on Monday or Sunday, you can use the muon length to measure the muon energy, because now it's contained. So the energy resolution on muons in Deep Core is actually quite good, on the order of 10%. The directional resolution is quite bad. I will put it on the 20% or so range. And then you can have some amount of flavor identification, where you can separate between tracks and cascades too. So the energy is better than the high energies because of the nature of the physics, but the directional reconstruction is certainly fairly worse. I don't remember how well the upgrade is going to help on that. I don't have a plot, but I can look for that for you if you send me an email. But certainly with the upgrade, our efficiency is going to significantly improve to be good at order a handful of GeVs.
And you do with those templates for the amount of deposited? Because
Sorry?
you showed, I don't know what day, that you had each PMT and the amount of energy deposited, I don't know, number of photons
Yeah.
deposited for each, and then you average out and then you compare to see what it is, and you do it the same way here.
Oh, yeah, okay. So you're talking how we're going to do the reconstruction of each one.
Really doing it.
I think we're not going to do that because now with these machine learning tools, it's so much more efficient to just have the machine predict us directly the distribution of photons in every one of them. And one thing that's more complicated is that in these second generation detectors, you actually have many PMTs in all of them, right? So now it's not only what you see in one PMT, but what you see in all of them. So that's going to be challenging, but we think that these sort of machine learning efforts are the way to go, probably.
I have one question. Following what you say about the P1, can you see the double bands better in the P1? Because this large spacing?
Yeah, I think that's going to be probably not so good because the spacing, it's more dangerous because you have background. For example, you can have like a muon that hits like here and here. And so when you don't have a contained detector, your background rate for double bands should be worse. It's not very clear. I haven't seen somebody done like a very detailed estimations of the backgrounds and efficiencies of different water versus a detector for double bands. So most people have focused mostly on muon neutrino optimization. But my guess is that because you have holes, that's going to be difficult to be sure that, I mean, the concern is that you have something like a, a muon that comes like that, and at the same time from like a mu interaction, right? And so this could be a cosmic muon, and it accidentally looks like a double band signature. So that's going to be tricky with holes.
Questions?
Hey Carlos, thanks for the lecture again. You commented a bit about the prompt atmospheric flux.
Yes.
We haven't really measured it. And also that we have this very low number of tau neutrino candidates.
Yeah.
If I'm not mistaken, we are going to do measurements about charm production of taus using phaser null in the next few years.
Yeah.
How would they improve the prospects for detecting tau neutrino events in IceCube in upgrades, if they do? And could we hope to reach a point to maybe be able to see some distinction between what you would expect for normal tau neutrino events and maybe some exotic tau neutrino events from new physics or other contributions?
Okay, so the question is again twofold. So one of them is we have measured this D meson flux from D mesons. There is an experiment called phaser nu, which is going to be along the beam line at CERN. That's going to measure forward neutrinos. So that's going to help constrain the uncertainties in the calculations of D meson production, because it's a similar phase space. Tau neutrinos from D mesons are still very, very small in rates. I think those are always going to be subdominant given our efficiencies. I don't expect that we will ever see those. We will, let me say this in another way. Before we see those, we should see D meson neutrinos in mu neutrinos and electron neutrinos, because those are a factor of more than 100 times larger in flux. Okay, so the observation of D meson neutrinos will probably come from electron neutrino measurements, where the D component is the highest. The second, so I don't expect that to be a background. So when we're talking about tau neutrino searches, those are going to be exclusively astrophysical neutrino measurements. But when we get to seeing hundreds of tau neutrinos, we are going to get to another interesting point, I think, which is to maybe have it somewhere. Maybe it's, what did I talk about this? Here. So when we start measuring lots of tau neutrinos, you can eventually start measuring this process. So you can start looking at top production. Top production is actually much larger than that D meson, right? Because this is 10% of the cross section, and this W, you know. So when if you were to have hundreds of those events, you could start looking at that. I think this will happen before you actually see the taus from D meson decay. You will probably measure these processes through the earth.
Thank you.
No questions? No?
There is one question here.
Yeah, just following up on what I asked before. Would you say that doing the reconstruction of either the energy or the arrival direction with machine learning is an okay thing for a physicist to do? I mean, in terms of...
That's an interesting question.
Yeah, I mean, in terms of... Because you're using an algorithm that you don't really know the exact shape of the function to do physics.
Well, but you have calibrations, right? So, okay,
Yeah.
so this is like a more
Yeah.
philosophical question.
Yeah, I want to know what you think about it.
I think that you have to be very careful. So let me be clear that you have to have your detector well understood and calibrated, right? So that's why we have in situ calibration devices to understand the light emission from, like when we have an ice cube dome that can shine light, and I can use that to calibrate the ice properties and my detector efficiencies, right? So first you have to calibrate things, but more of the data are calibrated. I think that's okay because you can use things, for example, as the cosmic ray moon shadow. So we know that the moon actually attenuates the flux of neutrinos and cosmic rays in that direction. So you can actually reconstruct the moon position, and we know where the moon is. And so you can use that to be sure that your algorithm is actually working. So I think that would be okay.
But how do you estimate uncertainties?
So
in
you
your
have an uncertainty
reconstruction
estimation.
with
which-
machine learning.
So you have an uncertainty estimation, which you claim is how much error you should have in your neutrinos, right? That translates to a significance of observation for the moon, right? If your uncertainty is incorrect, you will mismatch your distribution of neutrinos in the moon direction, right? So I think that calibration will work quite well.
Okay.
Yeah, I'm not that concerned about that.
Not? Okay, thank
No.
you.
I mean, we have been using things like BDTs and other black boxes of different types for 20 years, and you know, I'm not that concerned. But you have to be careful with any ML methods. But yeah.